Yeah, okay, so I'm going to tell you a bunch about Lean. I know from yesterday's introductions that there's an enormous spectrum of experience with Lean in the audience here, from some people who've never seen it to some people who are serious experts. So I am going to start at the beginning. But I'm also, as well as giving a little demo of what it feels like to work in Lean at the beginning, I'm going to talk a bunch about how the Lean community works and how projects using Lean work these days. And depending on how much time I have at the end, I want to show you just a few examples of the extensibility of Lean and the sort of directions that we can go with the technology over the next couple of years. Before I get started, though, I realized that while everyone was talking about their databases yesterday, I forgot to mention one database that I was involved in years and years ago, which is the Not Atlas, which is a great database. Anyway, okay. I'm doing something, sorry, I have to change resolution a bunch here to make all this usable. How big do we go? Okay, I'm going to do something, oh dear, sorry, there's a bit of a time delay here. I zoomed a bit too far. Okay, I'm doing something completely reckless and irresponsible here because this system that I'm showing you here doesn't have Lean installed, and I'm actually going to install it as part of the demo, okay? Just to show you that, like, this is, fingers crossed here. Okay, so what I have here is VS Code, which is a fantastic code editor. We don't need anything else. This is the recommended platform to use Lean in. If you really want to use Emacs and Vim and various other things, you can, but VS Code is where we encourage everyone to be. Okay, so you download VS Code from the website, you go to the extensions menu, you type Lean 4, and you click the install button. It says installing, and then a little tick comes up saying installed. Okay, that was pretty good. You then get a button in the top right, which is a little for all symbol, and you click on that, and you say new project, and we're going to select create project using Mathlib. So Mathlib, as we'll talk about later, is the main mathematics library for Lean. You don't need to use it if you just want to do programming in Lean or you want to really start from scratch, but nearly everyone is going to do that. So we click on that. We tell it a folder we want to live in. Oops. Demo, and we click OK. It does some stuff down here. It updates some things underneath. It does some installing. Fingers crossed this doesn't take too long or break horribly. We'll see. Okay. This was so much faster than we did it yesterday, of course. Oh yeah?
Maybe still happen? But I have one thing I forgot to announce.
Yeah.
We have our lightning talk selected for after this talk. I can't read it, but I wrote it down earlier. If you're on there, you're talking. Can you read it, David, or could someone back there read those names off to me?
Got Oscar, Valeria, Gloria, David Rowe, and Ben Nuts.
All right, and Ben, we may or not get you to you today, but those are the ones we have queued up for after this talk.
Okay, so what you can see happening here, it's downloading a whole lot of stuff in the background. This is just downloading all of the precompiled artifacts for all of Mathlib so that once this gets to 100% right there, we're going to have everything set up. And it wants us to click Open Project Folder. And here we go, we're in a brand new project, ready to start doing some maths. Notice in all of that, still not quite there. There we go, we've got some files. Click on AIM demo. And we've got a Lean file up and running. Let's just make sure that the basics are there. There we go, 2 plus 2 is 4, okay? So something that you'll see anytime you're in a Lean session, there's 2 panes to the editor. There's where you write your stuff, and there's over here is where Lean talks back to you, okay? The one thing I just want to have everyone notice about this, we just installed Lean, and there was no command line involved, okay? It was all, this is new, as of really just the last month, but it's awesome. Okay, let's just import all of Mathlib, because at the moment we don't know what it is we need. The yellow bar on the left that you saw there meant I'm thinking. Mathlib is pretty big, there's 1 million lines of code there, but notice that that yellow bar wasn't actually up there for long. We imported 1 million lines of mathematical development in a couple of seconds. Okay, let's try and prove something. Oops. So here I'm going to say, we're going to prove Euclid's theorem, the infinitely many primes. Maybe, I'm not sure that actually might have passed too fast, but notice here when I said n colon natural numbers, I just typed /nat, and when I pressed space that turned into the nice Unicode symbol for the natural numbers. Sorry, let me make this even bigger. And generally just the conventional text shortcuts for all the symbols of what you type, and it magically turns into the symbol that you hope for. So what do we want to say? So we've got some natural number. Oh, let's write it with a for all statement. Okay. So for all. Oh no. Oh no. What am I doing wrong?
/all.
This is a disaster. Sorry.
Is it supposed to be in a parenthesis or not?
No. It's meant to just work. Oh dear. Okay.
The name of live demos.
Okay, for now, let's just write the word for all. Sorry about that. For all n, a natural number. That one worked. What do we want to say? There exists. Oh, it's really not going to let me do anything. The moment I said anything about the auto-completion of tech things, it stops working. Okay, there exists a p. Let's see. So let's see. So p is bigger than the n we chose, and p is prime. And we're going to prove this by using the magical keyword sorry, which lets you prove anything. And I'm just going to open at the top here the namespace associated with the natural numbers, which should help us. And a little syntax error, the red highlighting there, I read a comma there, but I really needed to write and that one. Okay, so now if we put the cursor in front of the sorry, over in the right-hand side, it tells us what we're meant to be doing, which is, well, it's just repeating back the statement that we gave it so far. Okay, so what are we going to do? I'm going to just take the usual proof where I'm going to take the n I started with, I'm going to take that factorial plus 1, or pick a prime factor, and then everything should fall out. Yep.
Just as the goal on the right, you got just by placing your cursor somewhere, you didn't have to do anything else.
Yeah, just placing cursor. Yep, popped up. Yep. Okay, so let's see. The goal on the right-hand side is a for all statement. So I better run the tactic intro, which introduces that variable. And let me name it, actually. Let me write intro n. It got an automatic name, but it's generally better if you pick the names yourself. And then what do I want to do? I want to let, let's call it big N, be factorial n plus 1. Okay, and so now we've got in our context this extra hypothesis, big N, which is n factorial plus 1. Okay, so at this point, I want to pick a prime factor of that n, and, well, I don't know what to do. What's the code for picking a prime factor of a number? And this is a general problem in all interactive theorem provers, discoverability of theorems. We have a bunch of tools. Let me just demo this one called Moogle, made by some people called Morph Labs, who are a small AI startup who are working with Lean. And they gave us this kind of cool tool. Choose a prime divisor of a natural number. You just type some natural language, hit enter, and it pops up a bunch of suggestions. What's this one? Okay. Oh no. The one I wanted was like the second option when I did this this morning, and now it's not there. Okay, let's give it. What's that?
Ask again.
Ask again. Yeah. Okay, fine. Let's actually say let's ask it for the smallest one. Oh, and there we go. Okay. It says yes, it's nat.minfac returns the smallest prime factor of some natural. Okay. So let's do that. So let's let P be the minimum prime factor of n, and again that appears in the goal view as an extra hypothesis. Okay, maybe let me say one of the things I want to prove. I want to prove at this point that P is prime, and so I'm going to enter a little sort of sub-environment here. I use the have statement to say I want to get this particular intermediate target, and then notice the cursor's indented a little bit. I'm in a smaller proof environment trying to prove this fact that I've said I want to prove. But at this point, I mean, this should be easy because, like, I chose it to be a prime factor, so surely it's going to be prime. So this is not part of the main argument in some sense. So let's leave it for now. I'm just going to write sorry. This part's got to be easy. Let's get on with the difficult part. And I think this is a good principle, writing because you always do the difficult stuff first, leave the stuff that should be easy for later. Okay, so we've got that. We chose it to be prime. So what are we meant to be doing now? Well, one thing that we should do is type use P, which, if you look how the goal changes, before the use P, it was an existential statement, and after the use P, the existentials disappeared. We're just saying use this as the witness of the existential. And the goal now is just some conjunction of two statements. So we use well, it's a bit unfortunate that this is the tactic. It's called constructor, which is maybe something only a computer scientist or type theorist would love, but it just means we're going to prove the two halves of the and statement separately. And now there are two goals in the goal view. You can just proceed writing a sort of linear chain of thought kind of proof here, but it's often nice to use structured proofs. We've got two goals, let's deal with them separately. And so the bullet point lets us into the state where we're focusing on the first goal, one at a time. Okay, how do we, so now we're just meant to be proving that P we chose is actually bigger than the N that we started with. We remember that we're meant to do this proof by contradiction, so we type by contra, and that introduced a new hypothesis. It is not the case that N is less than P. Our goal is now to prove false. That new hypothesis that was introduced, notice it had this little tombstone symbol next to it. That means it's an inaccessible name. It's a name that we didn't choose ourselves, and so it might overlap with other names, and we should be careful with it. So it's probably better that we just give it a name. So we'll write by contra H, so we can refer to that hypothesis if we want to in future. And notice the hypothesis is a bit annoying. It says it is not the case that N is less than P, which is obviously meant to say P is less than or equal to N. There are a bunch of ways we can achieve that, but a common theme in lean tactics is there's an exclamation mark version of many tactics, which just says, do the basic functionality, and then try a little bit harder to clean up and make life easier for me afterwards. And so in that case, by contra exclamation mark, it just tries to push negations further into statements after it introduces things. Okay. So, what's the mathematical argument at this point? We've now got to the good bit. So what is it? The contradiction arises from the fact that, let's see, so P has to divide n factorial because it's in most n. It also has to divide n factorial plus 1 because we chose it that way. Therefore it divides 1, but it's prime, so everything falls apart. Okay, let's see if we can do that. We can use this neat tactic observe, where you just say what you want. Let's see, P divides N, and we just magically now have this fact in the goal in the state that minfac N divides N. Where did that come from? So notice I didn't write a proof there. I just said, hey, observe. You can look under the hood. Observe has a question mark mode. So like there's an exclamation mark mode that tells a tactic to try a bit harder. Question mark mode often says, explain what you did in this tactic. And it gives a suggestion over here. It says, try this. Have P divides N, colon equals, minfac divid N. That is, it's the theorem that the minimum factor of something divides the thing that you started with. And you can just click on this suggestion and it replaces it over in the editor, if you like. But for now, let's just go back. So let me get rid of Moogle.
Kim,
Yes?
what's the difference between observe and have?
So observe you can just write without a colon equals. That is, you don't have to give the proof. So what observe is doing is looking through the entire library, everything you've got imported, which today is actually all of MathLib, and trying to find if there is a single theorem in the library which proves that conclusion, possibly after filling in arguments of that theorem using local hypotheses. So it's essentially a library search tactic. Observe you would never actually use in a proof you committed to a repository because it's doing this expensive search under the hood. You'd always replace it with the explicit version. But in a demo, it's fine. And we just keep going. P divides factorial n.
Not factorial, capital N.
No, excellent, thank you. It didn't find a solution, but now it does, because I said the right thing. Good, okay. We just keep going. Observe P divides 1. Great, no complaints. Observe that it is not the case that P divides 1. We've got everything that we need. We've got a fact and its negation. Maybe I don't remember, though, what the tactic is that finishes from here, even though it's really easy. So we can type hint. Maybe that's a bad... I'll show you hint in a moment. Let's just type contradiction. We'll come back to hint. Okay. Okay, contradiction just found the fact that we have a hypothesis and its negation in the environment at the same time. So we finished there. We enter the next bullet point. This bullet point, of course, we've already done. This was the fact that it was in our have statement at the beginning. Maybe we'll write hint here. It suggests that you should just say exact this. Okay, that's fine. Notice that there are no red squiggles anywhere in the proof now. There are no errors that it's complaining about. There's a yellow squiggle right back at the beginning, and that's warning you that the declaration uses sorry. We've still cheated. Yep, so we've still got to prove that P was prime. Now, how are we going to do that? Well, there are a bunch of things we could do.
Can you observe P prime?
Well, that's a good question. Yeah, let's see what happens if we just try observe. So it says observe did not find a solution. And we'll see in a second why it's not just a lemma application, a single lemma application given the current environment. There's a tiny bit we need to do here. Okay, so again, we're in the situation where we need a lemma from the library. Show that nat.minfac is actually prime. See if Moogle comes up with anything. And it does. Okay, that sounds like a very plausible statement. The theorem name is minfac underscore prime. You're maybe getting the sense that we have a very standard naming scheme for all theorems in Lean, and often if you just know the syntactical statement that you're looking for, stringing together the components of the syntactical thing you're looking for is the name of the theorem. But we can also just read here. I mean, the statement is saying that minfac n is prime, okay? Another thing that we could do is there's the apply question mark tactic, which goes and searches the library for relevant lemmas that don't necessarily close the goal, but can be applied to the current goal. It gives you a bunch of suggestions. This one is a kind of random, something about arithmetic functions. I don't know why it thought to suggest that one, but second on the list there is the one we're after. And that then replaces the goal with the much easier fact that n is not equal to 1. Okay, you can see we observe didn't work because it's not a single fact. Like n is not equal to 1 is not in the current environment, but it should be an easy consequence of n being n factorial plus 1. There are a couple of ways we could go here. We could either go and look in the library for lemmas that tell you that factorials are positive and build up the inequality that way. We could also just try typing hint, thinks for a moment, and it gives a bunch of suggestions. Notice that for each of these, none of the hints actually close the goal, because after each suggestion is given, it's told us what the remaining sub-goals are. Well, I don't know, simp is just a simplifier, and it's nearly always a good idea to simplify if you can. So let's just click that suggestion. And that didn't change much at all. It just moved the, I guess it cancelled a 1 off either side of the equation and moved the not out to the front. But okay, that's still progress. Let's type hint again. And this time it says, you can just use exact. Factorial is not equal to 0. And we're done. And now that sorry is redundant. There are no goals to be solved. So we just delete it. And we've got our proof. Okay. Any questions? Okay. So obviously this was a fairly artificial proof. It was a kind of curated to be able to show you a few things along the way. It's not necessarily representative of the actual experience, but it's an indication of some of the sorts of things you have.
Kim, I just have a quick question.
Yeah.
So in refine min fact prime,
Yeah.
what does that say on like 2 bar?
Yeah, sorry, let me zoom one more step. Get rid of Moogle. Yeah, so maybe we could have, an equivalent and simpler thing we could have written here is just apply minfac underscore prime, which says, which is saying, I know that this theorem, that the conclusion of this theorem matches the goal. Please try and unify it with the goal until many arguments that are needed. The thing that we had before that the automatic tactic suggested was refine, and it has this unusual question mark n1, which is what we call a named hole. So this is saying, I want to use this theorem, and I'm going to fill in the arguments for you, but some of them I'm going to fill in with holes. And what happens is that after you apply that theorem, those holes become new goals afterwards, and they get given names according to what you wrote after the question mark. So that, for example, if you have many goals, you can select the one you want to work on, rearrange them, things like that. So if we'd written question mark H, the goal would have been called case H instead of case N1 after that.
Okay, thank you.
Okay, 2 things there that I really wanted to include in this demo. One was these observe and apply question mark and hint tactics, which are all things that help you find stuff. And I also wanted to show you Moogle, which helps you find stuff in a rather different way. The reason I wanted to show you those things is because these are hard problems, and it's one of the most painful points of using an interactive theorem prover. Finding theorems is hard, okay? So we have a bunch of tools that help, but it's still hard, and this is still a problem. Okay. That's the first demo. Let me quickly just draw a little bit of a picture of what the lean world looks like at the moment in terms of. Oh yeah.
So imagine that I'm a beginner.
Yeah.
How do I learn all these tactics?
Yeah. So the way you learn all these tactics is by starting here at the natural number game.
No, I want the documentation of that.
Okay, so Lean has just gone through this this giant phase change where we moved from Lean 3 to Lean 4. There was this massive project to port the entire mathematics library from Lean 3 to Lean 4. We finished that just a couple of months ago. It feels like longer than that. Conspicuously, the nice documentation for every tactic kind of got lost in that change. And at the moment, this is a big hole in our documentation. We're working on it. There is not a central entry point to a list of all of the tactics with clear explanations. We do have a bunch of things like there are cheat sheets for people coming from other languages like Coq and so on, giving you basic translations. We need to work on it. Rob, yeah.
The Lean 3 tactic list is still up, and it's not entirely accurate for Lean 4, but it's like 90% accurate.
Yeah.
So that would be my suggestion if you really wanted the list.
Yeah. There are a few other, so I mean, the natural numbers game is the place to start if you're a beginner. There are a bunch of different tutorials and ways to get into Lean. Different ones take very different viewpoints and starting points and are aimed for either computer scientists or mathematicians or somewhere in between. But the book Mathematics in Lean is excellent. It's addressed to mathematicians, and it has a sort of tactics-first orientation. It doesn't try and write term mode proofs, it writes proofs the way that I was just showing you now. It's a good place to start. Okay, sorry, quick diagram. Okay, so at the top, there's Lean itself, the programming language, the compiler, the interactive theorem prover, whatever you want to call it. It is important, especially now that we're in Lean 4, it is a programming language and an interactive theorem prover in some sense only secondarily. And it's a good programming language in a lot of different directions. And one thing is actually that it's fast, in a sort of surprisingly fast. And it's worth keeping that in mind. Okay. Below Lean itself, there's what we call STD. That's the standard library. It's primarily intended for programmers. It's a standard library in the sense of a programming language standard library, but it also does include a lot of tactics, sort of tactics that everyone would like that aren't mathematics specific. Underneath that, there's, I need to draw a sort of giant bubble for this one. There's MATLib, which is the main or the central mathematics library for Lean. Yeah.
So you said that standard contains tactics for programming. I've
Yeah.
only ever heard tactics described in the context of automated theorem proving, so I don't know what it means to do a tactic in a programming language.
Okay. Yeah, so, okay, maybe I should have said tactics for verified programming, but that said, I mean, you can construct data using tactics. I mean, often it's a bad idea, but sometimes it's a good idea. I think it's true. Maybe we can talk about that later, what exactly that distinction is. Okay, so MATLib is big. I didn't actually look, but it's well over 1 million lines of code now.
1.4.
Sorry?
1.4 million.
1.4, okay. And it's growing fast. Yesterday someone was asking, like, how fast? And I said, oh, there's about 20 pull requests a day that get merged. And I was worried afterwards that I'd just pulled that number out of a hat and maybe I'd overstated it. But I went and looked last night, and in the last 7 days, there were 141 merged pull requests. So I nailed it pretty exactly. So one way to think about that is that to do continuous integration for MATLib, we have to merge PRs in batches because we couldn't be running CI fast enough to merge things linearly. Like we're merging stuff faster than we can run CI. It's kind of, yeah, it's a bit out of control. There are good things and bad things about it being massive. The good thing, well, there are several good things. One, everything is in there and it's all compatible. You want to use single-atomic numbers and differential equations in the same argument, fine. Like we promise that they'll work together. Another good thing is that it's maintainable and maintained. Once things are in MATLib, they stay in MATLib, and as things break, they get unbroken again. There are some problems. I mean, there are some difficulties managing a community that large and managing the infrastructure for it. And it's also, by necessity for being such a big and general library, often it's at very high level and very abstract. You won't find vector spaces in MATLib. There's a huge amount of linear algebra, don't worry. But we just start with modules over a ring, and a couple of the theorems happen to be about what happens when the ring is a division ring or maybe even a field. But when you can do it generally, we do it generally. And that can be kind of intimidating for a beginner. An undergraduate who wants to come and contribute are the vector spaces. Okay? It's a slightly unfortunate consequence of the size and abstraction of the library. Okay. Off in different directions, there are many other libraries. Some of the things I've written there are sort of major automation tactics, which can be used for either verified programming or for doing mathematics. But there's other things here. There's like command line parsing libraries, and someone is writing a wrapper around libuv to do all I/O operations, things like that. Okay, so the stuff you'd expect in a programming language ecosystem. This part is all only developing, but it's growing fast. And then there's a bunch of projects sort of underneath MATLib. I mean, there are many underneath MATLib, but I'm just going to mention a few of the big ones. So there's the liquid tensor experiment, which you may have heard of, but maybe I'll mention briefly. There's this sphere reversion project, which was kind of cool, demonstrating that you can do sort of it's not just abstract algebra and category theory and number theory that you can do in Lean. You can do geometric topology, talk about differential equations, do all that stuff. I'll talk about this very new project, PFR, and Kevin Buzzard's got a big new grant to tackle Fermat's last theorem over the next couple of years. We'll see how that goes, but that's obviously a massive project.
And those are all contained in the MATLAB monorepo?
No. So this line here was we're moving to different Git repositories now, separate things. They all depend on MATLAB because they need the definitions, they need the theorems and so on. And I'll talk about how these chains get established in just a moment, like what it looks like to build one of these on top of MATLAB. Okay, a little bit just about sort of structure. So there's this new organization called the Lean FRO, it's Focused Research Organization. These people called Convergent Research put together these FROs. They're all on the scale of 10 people, 5 years. They're intended for research projects that somehow fall in between industry and academia. I like to say that they're not quite ready for commercialization, so industry doesn't want to fund them. On the other hand, stuff actually has to get done, so it can't be done in academia. That's where the FROs come in. And the FRO is largely focused on these parts, but we very much care about MATLAB and want to make life good for the people using and developing MATLAB as part of that. But we're also extremely interested in all this stuff here, making Lean a viable general purpose programming language and used outside of proving theorems as well as in mathematics. And then all of sort of this part, well, sort of gets fuzzy at the bottom. But there's the MATLAB community that manages MATLAB itself. If you're going to merge 20 pull requests a day, obviously you do need some structure. There's a whole team of people. This is the web page for the community parts of development of Lean and the MATLAB library. This is the place to go if you want to get started. It has tutorials, running Lean in a browser, links to papers and courses, all of those sorts of things. The maintainer team, I didn't count, but it feels like it must be at least 20 of us by now. These are the people who are in some sense like the editors of this object. They're the people who've got to approve a pull request before it goes in. There's then an even larger team of designated reviewers anyone can review a pull request, and we encourage everyone to review. But essentially, the reviewers are people that we trust. If they say, yes, this is good, the maintainers just click merge and don't necessarily need to check anything themselves. There's maybe, I'd guess, another 20 people who are designated reviewers beyond the maintainers team. And then these larger projects downstream are a combination of people from the MATLAB community and sort of outsiders or newcomers coming along and developing projects further downstream. Okay, so that's what we have here. Okay, mathematics in Lean. This is the textbook I mentioned earlier. Highly recommended as a starting point after the natural numbers game. So the liquid tensor experiment was one of the first big external projects. Sorry, I shouldn't say that. It's one of the biggest external projects so far. So this was posed as a challenge by Peter Schulze, a theorem that he thought was pretty important, but he had some doubts about. He wasn't entirely confident the proof was right. He'd written it up and sent it out there, and he knew that despite a bunch of groups at other universities running seminars on it, trying to go through the proof, he knew that no one had really actually checked his proof, and he wanted someone to really check it, and so he proposed it as a challenge to the formalization community. So this is the blog post that started it all, and there, half a year later, we have him saying, while this challenge has not been completed yet, I'm excited to announce that the experiment has verified the entire part of the argument that I was unsure about. I find it absolutely insane that interactive proof assistants are now at the level that within a very reasonable time span they can formally verify difficult original research. Okay, that was pretty, everyone was pretty happy hearing Schulze say that, and it sounds like he was happy too with having his theorem verified. The people behind that then continued on and sort of did everything. The part when he was saying that the whole challenge wasn't completed, well, a while later, the whole challenge was. And okay, that was the liquid tensor experiment. I'm going to, the same sort of mechanism that was used to coordinate that community effort has been used to greater or lesser degrees on these other projects. So I'm going to fast forward a little bit to one of these more recent ones to show you how that goes. So this is Terry Tao. So he recently put this result on the archive. I mean, really recently, like it was, I think, November 5th, somewhere around there, like a month ago now. This very significant paper, this about resolving this, I think you don't know how you pronounce that name entirely, polynomial Feynman-Rutzer conjecture, which has been a big deal for a while in sort of additive combinatorics. Yeah, they resolved this conjecture. Everyone's excited about it. And Terry said, okay, well, how about we formalize the proof? And he first of all did a little experiment by himself, just learning lean, but he did it very publicly, and it's interesting to read his write-up of how that went. But then they announced this lean project. So here's the web page for the lean project. So I don't know, it just includes the human readable statement of the result they're proving. It's fairly simple to state. It's going to involve a whole bunch of measure theory and Shannon entropy to actually do the proof. But what is on this webpage? Well, the key document that is on this webpage is this thing called the blueprint. So the blueprint is just a human readable account of the proof. It's not the same as the paper. So if we click in random spots, it has lemmas and proofs, and it has references to things. So it looks fairly like a human readable document, but it's pretty terse. It doesn't have all the discussion, and many of that proof actually has some details, but many of the proofs are extremely terse. The point of these blueprint documents, which I think have turned out to be essential for a major formalization effort in Lean, they sit intermediate between the original human artifact that you post on the archive and starting the formalization effort. They're just a reaccounting of the proof, but written by someone who is able to anticipate where the formalization difficulties will be, and is writing the structure of the proof in terms of how you set up definitions, what order things are done in, with formalization in mind. And it really seems incredibly helpful to have this intermediate document written before the serious formalization begins. Now, what this document further gives you, notice that there are all these little ticks everywhere. These ticks mean that at this stage, this lemma has been proved, and if we hover over the tick, we get the word lean there. We click on that, a little pop-up appears, which just tells us the name of the lean declaration in the Git repository that proves this theorem. Of course, we can click on it and jump to the documentation. Well, the hypotheses of this theorem are a bit of a mouthful, because it's like, this is in some sense like a standalone statement of whatever this lemma was, all of the inputs that were needed to set up this result, and then, well, here's the statement. And you can click further if you want. You can always jump to source, and you get some actual lean code. That's kind of horrific. I chose badly, but anyway, second estimate, and off we go. Okay, look, you can see this. Whoever wrote this theorem really liked have statements. It's a giant collection of have statements, from just developing more and more facts from the hypotheses until you get to where you want it to go. Okay. The really cool thing that a blueprint document gives you is this graph, which unfortunately is kind of boring at the moment. Sorry, yeah.
What parts of what you just showed us for the blueprint on were written by a human? What was generated?
Essentially everything was written by a human in what I just showed. Yeah. So the blueprint itself, I mean, it's Terry Tao sitting down writing tech. It's just some tech plugins that generate the blueprint webpage. The lean source file I showed you with 100 have statements. Yep, that's just a human reading the proof, translating into Lean.
Yes, I have a related question here. So is it conceivable that one could author one's, like as a just ordinary mathematician, writing a human readable document for publication, is it conceivable that one could structure that in such a way that the blueprint could be at least semi-automatically extracted?
Yeah, sure. I'm not sure that I can point you to an example of that, but I mean, maybe Terry's next paper will be an example of that. I mean, there's no particular technical obstacle to extracting this blueprint web page, generating these documents from a normal tech document. I mean, that said, like this point I was trying to make that it does seem helpful to rewrite out your argument with formalization in mind.
But maybe the future should be that we write our papers with both human readability and formalization.
Yeah, I mean, quite possibly. I think we haven't seen a really good example of that being done yet, so we're going to have to see. So far, the successful examples of these big projects have always had an intermediate document.
Can we go back and take a look at the documentation page, so like link to the
Yep. So here's this is where you wanted.
no, the human lean. Yeah, click that.
Click that. Okay. So this is some different theorem than we were looking at before.
So like this is generated from.
Oh yeah. So this document, this here is automatically generated. Sorry. Yeah, you're right. This intermediate documentation page is pulled out of the lean file.
And is this sort of the norm? Like if I wanted to like show the proof of this fact in lean, is the normal thing there to like link to the published documentation for the for their standards practices?
Yeah, so I mean, this is a tool. It's just a tool called DocGen that builds these web pages. There's no customization per project for that. Yeah, I mean, people often it's academia. People need to get publication artifacts out of things. So there's often an archive paper that goes along with the formalization effort. So maybe you link there in preference to the documentation page, just because you want to generate links to your publication. But yeah, you can choose.
I guess in particular, this tau minimizes name is like a stable identifier.
Yeah. There's nothing in the system that enforces that. People can go and rename. In MathLib, we're extremely strict about names. This is one of our principles. We have a very boring way of naming theorems, and we name them that way. And so that results in fairly stable names. We could be more stable, yeah, and I think that's...
I guess like about using theorem, like is this tau minimizes homepage? You know?
Yeah, this is tau minimizes homepage. Yep, absolutely. Okay, so the reason why a moment ago I said that this dependency graph is boring is because it's all green. Let me jump back a little bit. When was this? 18th of November, so like 2 weeks ago, 2.5 weeks ago. It looked more like this then. I'll zoom in a little bit so you can see. So what's happened here? At the bottom of the page is this statement labeled PFR. That's the final result of the polynomial Feynman-Rutzer theorem. And then there are all these intermediate facts. Some are round, some are square. I think the distinction is that square things are definitions, round things are theorems. There's highlighting in all different complicated ways. Notice things have both fill color and boundary color. Green things are things that are done. Blue things are things that are ready to do, in the sense that all of their immediate precedents are done. The fill color is the actual proof is done or ready to do. The boundary color means the statement is ready to do. That is, it is possible now. So like the blue outline here means that we have not written down either the statement or the proof of this theorem. But it is possible to state the theorem now in Lean because all the definitions required to write the statement are ready. And so someone can look at the blueprint, scan through it. This information about what is ready to do is reflected there in the blueprint. See some theorem that they understand or that they like or something is in some particular state, it's ready to formalize or it's ready to prove, or they can find that information is in this graph. You can click on this, you end up in a Lean editor by clicking in the right places, and you can prove the theorem make a pull request, and the graph updates again. So
What is the my hat?
No. This graph is generated automatically from in your text file, you have, like when you write /ref theorem : blah, that generates an edge in the graph. Yeah. So this is pulled entirely from /ref statements in a text document.
What about the fill status?
And that's pulled automatically from looking at the lead repository, compiling it, and checking which no, that's not entirely true. What is true? No, that's the full status is less automated than it could be at the moment. That is drawn from the text document, and it requires people adding the hyperlinks to the statements of lead. The boundary is always going to require some human input to say whether the statement is ready to be formalized or not. The fill status, of course, you could pull automatically from the repository. Are there sorries in this proof or not? But I think that's still manual at this point. So the picture I was showing you a moment ago, I've lost it. Where was it? Is really boring because it's all green, and I'm pretty sure that last night it wasn't all green, and so they must have overnight finished the project. Last night PFR was blue, everything else was green, so we knew it was coming, but it seems like they're finished and the project and the dependency graph just got updated. So hooray, congratulations.
About 6 hours ago, I think.
6 hours ago, great. This stuff goes around the clock. I don't know how many people contributed to this one. It's probably on the order of 20 or so people, maybe a bit more. But one thing I want to emphasize is that this work is extremely parallelizable. Once you've got this blueprint document and the dependency graph, different people can jump in all over the place on the graph. And you have lots of really rich feedback about what they're doing. Lean is checking whether they've proved the statement that you thought they were going to prove. Yeah, it's checking that the theorem really was correct. The PR is being, like when they make the PR to the Git repository, it gets compiling everything and verifying that there are no errors and that Lean accepts everything. I don't think there's a sort of, you've probably all heard of these polymath projects. They're kind of awesome, but this I think lets you scale even bigger in some ways. Okay. I'm just going to finish with a few demos, a few very short demos, sort of mini lightning talks of just some sorts of extensibility that you can get out of Lean. Especially Lean 4 is intended to be an extremely extensible language. You can do all sorts of stuff with it without needing to bother the core developers. Let me just show you a few fun things. Let's see. Oops. So the info view is that thing on the right that shows you the proof statement, but it's just a web page, and you can run JavaScript in it, and that JavaScript can talk back to Lean and inspect the proof state and modify the proof state, do whatever you like. So here, I don't know, we've defined some statement in Lean, which is some word in the Rubik's Cube group, and I mean, why don't we just render it, okay? No problem. That sort of stuff is easy. You can do whatever you like. Similarly, what's the other one I wanted? You can, this is just another sort of demo of things you can do in the goal view. Here's some extremely boring sort of category theoretic statement. I have some morphisms F and G in the category of types from the natural numbers to bool. And I want to prove that F composed with the identity morphism on bool is equal to G composed with the identity morphism on bool. Okay, idiotic statement. But you can just say, hey, Penrose library, please render the commutative diagram that this equation is representing. Okay? And you can have whatever sort of extra structure or extra animations you want in the goal view. And these can be interactive. This example I'm showing you is not, but there's no reason why we couldn't be able to like click and drag in this and have our actions in the rendered goal view be translated back to tactic steps in the proof script on the left. Okay, and there are a bunch of examples of that already, where like you can do focused rewriting, like zoom in on a piece of the term in the info view and say, I only want to rewrite this sub-expression instead of rewriting the whole thing, and it automatically generates proof terms to do those things. Similarly, this is sort of more in the direction of here we go. This is some stuff people wrote to, rather than that the goal view, which just has a list of hypotheses and a list of the things you want to prove. There's now this sort of graphical representation of the proof so far. Here, you're meant to read this from the top. You have the initial hypotheses of the theorem when you started writing the proof. At the bottom, you have the goal when you first set out, and then it sort of builds in both directions as we either do backwards reasoning by applying lemmas to the goal and trying to fill in the hypotheses, or do forwards reasoning from the start, like introducing variables, having new statements, breaking hypotheses apart into components, and then things kind of merge in the middle. And eventually we've got to this sort of sub-goal where we have this fact, and finally they get unified, and you get this nice graphical description of what's going on. I think this paper proof demo at this point doesn't have any interactivity. You can't generate your proof by working over at this side, but I mean, the sky's the limit. If people are working on that, it's going to happen. In terms of, there's also lots of neat things you can do in terms of language extensibility. Maybe actually let me give a quick shout out here to, let me see if I can find it. Yeah, this is Heather Macbeth's course on Lean that she uses as an introductions to proof course, where rather than trying to expose students to the full-on experience of Lean with the whole tactic library, which we know is too intimidating and unproductive to try and teach students, she has written a very carefully curated tactic language that is sort of a separate implementation, essentially, of the tactic language, but that just gives her the things that she wants to show to students. And that sort of opens up new levels as the students progress through the course. It's very nicely done for people interested in teaching using Lean. This is absolutely one of the things you must read. But it's also a nice example of the fact that the particular front end that Lean gives you for interacting with, you can replace it with something else if you like. In the same direction, Patrick Massot has this thing that he calls verbose Lean, where instead of writing the sort of terse tactics that I was showing you before when we proved Euclid's theorem, you just write out what looks like pretty much like English, what you're doing. Let's prove that something. Fix some fact. By some fact applied to some other fact, we get delta such that some condition. Okay? This is not free-form English. You do need to learn the grammar of what phrases are allowed and how they plug together. But it's pretty flexible, and this is just standard Lean. I mean, you've told Lean a new way to interpret certain declarations, and the parser is flexible enough that it can just do this sort of stuff. And you can, I forget what other, you can do this in French as well if you want. And I think there's a pull request open that does it in Catalan. It's whatever you like. Okay, there's enormous flexibility to do things like that. Yeah.
Is there a translator between non-verbose and verbose Lean?
I don't. Maybe let's check with Patrick offline. Let me not answer that. Yeah. I think that he has thought about that. I think there's nothing that you could use, but yeah, it's been thought about. Yep.
So I could imagine when you're doing this that it might be really easy to leave out a word or something like that and get a possible error message.
Good question.
So the question is, are there like snippets that you can just drop in so that you just get it right every time, the phrasing?
That's a great question. To be honest, you have seen as much of verbose Lean as I have at this point. Yeah, no, sorry. I accidentally reloaded the window instead of restarting the server. I just deleted a word to try and see how badly things went. I don't actually read French, so I'm not sure if the word I deleted mattered or not. What sort of error message do we get? Yeah. What does it say? Oops. Unexpected token, expected something. Oh, the error message is actually really useful. Okay? Didn't get this word, you've got to say one of the following 3 things. That's pretty good.
Yeah.
There was another question there? Okay. Okay, yeah, it's also, I guess, one last thing. I mean, it's just a general purpose programming language. You can, oh yeah, sorry.
Yeah, so maybe this is a side question, so feel free to answer it later. But we're writing all these tactics, we have all these different tactic languages essentially. And my understanding is that when we write proofs with tactics like this, they get expanded into raw lean code in some sense.
Yep.
Is that raw lean code usually readable or usually a monstrosity that no one should ever look at?
It depends. When you use tactics like have and apply, you get very readable things. When you use things like the simplifier or rewrite, you get monstrosities that only a type theorist could love and are pages long. Yep. So it's very easy to generate proofs that should not be looked at by humans. Yeah. So it's a general purpose programming language. You can do anything that you want under the hood. So something that I put together. I'm not going to show you the implementation because it's disgusting, but it also only took like 5 or 10 minutes yesterday. Here's demo integrating with LMFDB, since that seems to be the thing we're doing. So I just implemented a command #LMFDB, and you give it a category, whatever you call them on the database, and a label. It goes and behind the scenes grabs the JSON for that thing, parses that JSON, pulls out something. At the moment, all that it knows about, because I took 10 minutes on this, is it knows how to pull out the A invariance of an elliptic curve. And then it goes and creates a lean declaration saying this thing equals the elliptic curve with those invariants, because MATLib has elliptic curves and a little bit about them. So this #LMFDB is a command that goes and executes code. It goes and interacts with the website. After it's run, this identifier is now in scope, lmfdb.category.label. I should have typed, an extra thing I should have written here is #check L. Oh man. Okay. So I'm actually running over SSH here because my laptop is 7 years old and not up to actually doing a demo. So everything is running on a server in Australia. That explains some of the weird things that are happening. Yeah, so when I write #check_L, that's just saying what sort of object is L in Lean. And so it's a Weierstrass curve over the rational numbers. Okay? So that declaration was built by #LMFDB. And then you can do things like we have you can calculate these B numbers from the A numbers. Very simple thing to do, but this number is Lean calculating those numbers from the A numbers that it pulled off LMFDB. And we've also got, there are various theorems. This is just some boring relation between various numerical identities, but you can specialize that general theorem, which works for any elliptic curve, to this one that we pulled off LMFDB. I maybe should have done something. I should have actually done some calculation with the group law, because that's one of the few things MATLib can actually do, but I stopped after 10 minutes. But yeah, if you want to do this sort of stuff, it's just like you write code in a normal programming language, but you can generate statements that you can then prove theorems. Okay, I think that's what I've got. Yeah.
So I'm wondering whether or not, so we have this now proven result of PFR, say.
Yeah.
And I wonder to what extent this depends on lean 4. So let's say that lean 4 becomes lean 5 one day. Will these non-MATLib proofs, but which depend on MATLib, be transportable, or is this?
Well, okay, we have no plans for lean 5. Superficially, you might think that lean 3 and lean 4 are not that different. The syntax has changed slightly. But to many users, it actually feels fairly similar. Underneath, they have very, very different things. And Lean 4 was written with a plan that it's going to be the thing for a long time to come. It's extremely extensible in lots of ways that Lean 3 wasn't. Okay, so put aside your fears that we're going to move to Lean 5. We can, though, of course, look at what has happened in the Lean 3 to Lean 4 transition. So MATLAB is huge, a million lines of code, and we translated that from Lean 3 to Lean 4. Partly we did that automatically. There's this amazing tool called Mathport, which is not just a string level translation of syntax. It's actually running Lean on statements and understanding the Lean expressions underlying the syntax and doing the translation at a fairly deep level. It required a huge amount of human work. Mathport produced all these broken files that humans then needed to go and fix up. But we got through a million lines of code, so Mathport got us a lot of the way. Mathport runs on other projects, and mostly people had to wait until the Mathlib port was finished before they could start on their other projects. That's only a few months ago. The Sphere version project has now been ported to Lean 4. It was entirely a Lean 3 project. It was finished before the port, but they've updated it using Mathport. LTE won't ever be. They've decided it's sort of end of life in Lean 3. They're not planning on updating that one. So it's possible, but it's a lot of work. That's the answer. This is one reason why there is some pressure to move things into Mathlib, because then you get carried along with the maintenance guarantee that Mathlib provides. But
source for the LMFTV demo up in here somewhere?
Oh, you do not want to see the source. It was really I won't show you. It's really incredibly gross. I worked out, you can still see in the code me working out the structure of the JSON. It's really gross. But it's just run curl, run json.parse, pull out the fields, run compile declaration with, I'll show you.
I'm more interested in the wiring up the LMFTV.
Yeah, okay. I'll show you. Okay. I copied and pasted from somewhere run command that lets you run a system process. Okay, here's run curl. Here's the command to, given a label, look up the elliptic curve JSON from the website using that label. Okay. Here is my really, really gross by hand JSON parsing as a one-off. I pull out that field, and if anything goes wrong, I panic. But this is a thing that you give it a label, and it gives you a list of integers. Okay? If anything goes wrong, it gives you the empty list. Good luck with what happens next. We check that runs. So we run get via Strauss 220.890.c1, and it spits back 5 numbers. Awesome. Little helper function that takes a list of integers and actually returns the Weierstrass curve. And then here's the magic that creates a declaration. So what does it do? We're setting up new syntax here. That's the lab command to define a new command. It takes 2 arguments, which should be identifiers. We do a little bit of parsing of those identifiers. We throw an error if the first identifier wasn't elliptic curve over Q. We run our command to go and get the numbers from the website. And then we call add and compile, which generates a new declaration and sends it to the environment, where essentially the interesting stuff is here, which I could have written in a much less obscure way, but the type and value there are constructing the type and value of the declaration that we want to construct. I could have used a quoting library to make that look prettier, but you do the obvious steps. And there's yeah.
Thinking about what problem does Lean solve? Do you have examples of how it has maybe changed how we do mathematics?
Yeah. Sorry. Absolutely. Excellent question. Thank you, because I meant to talk about this. A lot of people reach for the problem it solves. Is that we're not sure if mathematics is correct. Maybe there are bugs or whatever. and I couldn't care less. I mean, mathematics is as correct as it needs to be, and mathematicians in all different fields have chosen the level of correctness that is relevant to them. And if they need more, they can get more. And if they don't need more, they don't need more. I mean, if you want more, Lean can help you do that, but it's not necessarily a problem. I mean, the long-term thing is, which we're not at yet, is that this stuff is going to help us be better mathematicians. At the moment, so there's this sort of this formalization overhead factor. You take a piece of natural language, measure how many characters it is, formalize it, measure how many characters, take the ratio. Obviously that number is greater than 1 at the moment, significantly greater than 1, but maybe one day it'll be less than 1. And I mean, the idea is basically that you will be able to, at the moment, I talked about the sort of sorry structure. You start from the top level theorem, you break it down into lemmas, and then helpful people from the MATLAB community come along and prove those sorries for you. But as the level of automation rises, and as the level of AI assistance rises, more and more of those sorries get filled in by non-humans, either sort of old-fashioned automation or AIs. And we're not there yet, but increasingly we're getting to the point where it's actually useful. You only have to say, oh yeah, I know this, but it's going to work, which is a very familiar experience of having proof. And sometimes the computer says, sure, yep, I've got your back. And sometimes it tells you, no, I need more. And that's where we want to be. The other side, maybe from outside of mathematics, where we want to be. So one, I mean, we spend a lot of time talking to AI companies that are interested in doing reasoning and want to have Lean in the loop, essentially so that their systems have someone to talk to. You can propose chains of argument. Lean can say, nope, that's garbage, or yep, that's good, and that gives a feedback mechanism that doesn't require humans to manually evaluate stuff. I think that, moreover, I mean, code synthesis is a massive problem and opportunity. We want computers to be able to write not just mathematics, but write good code. They can at the moment, but they come up with interesting stuff sometimes. It is not helpful. But what many people are thinking about is that you will open up your large language model and give your human description of what it is you want your program to do. I mean, you write the docstring of your function before you start writing the function. It comes online. It doesn't just try and write the code. It reads your statement. It, in one direction, goes and tries and writes the code. But in a different direction, it tries to write the formal specification of the informal specification you gave it. Then it tries to complete that square by writing the proof that the program it wrote satisfies the spec it wrote. If it doesn't succeed, it knows it's got to go back and work on one or the other two, maybe ask for help from the human if it runs into trouble. But if it succeeds and can prove the program satisfies the spec, it doesn't even need to show the spec or the proof to the human. The human might not care or might not be qualified to read either of those. You can throw those all away and just give the code back. But it's going to be an awful lot better code than if it hadn't done that behind-the-scenes verification. And Lean is one of the sort of few games in town, I think, for that workflow, because it's early days yet, but it's a general-purpose programming language, and it's fast. You can do everything. But it's rich enough that you can describe arbitrary specs, you can prove arbitrary statements.
The workflow you just described, there's no reason why the code being generated needs to be Lean code.
No, yeah. That's, but it should be. I mean, I didn't really get to show this, but like, just, I guess I could actually in the PFR thing, but I'm out of time. A fantastic experience programming on a big Lean project, which is unlike programming in other languages. Say you go back and change some function early on in a massive development of 100 files. You change the definition, or you just change how some function works. Because Lean has just this extremely rich type system and is checking proofs, the little problems box at the bottom of VS Code will pop up a little error message saying somewhere deep down 100 files later, some proof doesn't type check anymore. And I mean, like the example yesterday, so just last night, I bumped the PFR project from MATLAB version 4.3 RC2 to 4.3. And some things had changed. Some theorem now had hypotheses that are about almost everywhere measurable functions instead of measurable functions, whatever. And when I did the update, they just get 6 little messages at the bottom, like the proof breaks in the following 6 places. And it's this also holds like when you're just writing code as well as writing theorems, but the fact that it so quickly pinpoints where things are wrong is very, very different from working in other languages. It's pretty fun.
What kinds of non-math applications have been made in Lean? Like, is there a web server written in Lean?
No, there's not a web server. Yeah, it's early days. I mean, for a lot of things at first, I mean, you shouldn't go and write things from scratch. Lean underneath actually compiles to C, and then we send it out to LLVM to finish the job. In fact, these days it compiles to WASM and runs in a browser if you like as well. But if you want to write a web server, you should, because Lean has got a great FFI, foreign function interface, you shouldn't be writing a socket library yourself. You should be writing a Lean interface to one, and that's maybe even by the end of the year that'll be out. But yeah, no, it's early days for a lot of that stuff. One of the people in the Lean FRO at the moment is working on a pretty amazing documentation tool that will let you write sort of text files with human readable text and Lean code embedded that renders to PDFs or web pages with live Lean in them, and that's all sort of written in Lean, of course. Yeah, it's coming.
So you said you would not rewrite the socket library in Lean, but is there?
I mean, you could, but
people,
like,
I know, but I mean, are people considering? Like, I would like to write a socket library where I have a proof that you can't exploit this. Is that
yeah.
a use case or no?
No. And definitely some of the early industrial users of Lean have been exactly doing those sorts of things. I mean, verified crypto libraries in particular are one of the places that industrial users have been thinking about Lean for a while. I mean, Amazon has a new project that's just gone up on GitHub where they do, they have, I mean, obviously they're very complicated in Amazon Web Services, sort of access control policies for all sorts of resources, and they want to be able to prove things about the access control policies that users set up to check that they behave as expected, and they're using Lean now to generate proofs of statements about things.
Another question. Do you have a sorry not sorry tactic that would attempt a theorem prover mode that just cranks out a 100-step proof with all kinds of facts?
So I didn't demo this now. So there are certainly people have fine-tuned some language models to generate proof steps just by like looking at Mathlib and seeing how that works with varying levels of success. I mean, Mathlib is big, but not that big compared to what machine learning people need to feed into their systems. Those systems, and then of course, and there are tactic front ends for those. So like I was showing you hint, which goes away and suggests the next step. There's like LLM step, is one that just takes your model and tries to suggest the next tactic. And there's not a user-facing version of this, but there are kind of prototype versions of tactics that do tree search over an arbitrary backend that suggests steps at any given point. These things are all at the point where they're fun to play with, and sometimes they produce good results, but they're not actually positive time savers in users' hands. But ask in 6 months, and that might be very different. I mean, a lot of people are working on this, and there are some companies that are putting quite serious amounts of money into doing proof search in Lean, not because they particularly care about Lean or because they want to help Lean users, but because it's a good environment to practice doing reasoning for AI. So we may not actually see from some of those companies something that mathematicians can use, because like we're not actually the end users they have in mind, but we might get some breadcrumbs to help with it. and they're putting some pretty serious resources into this stuff now.
For MathLib, what areas of mathematics do you feel like it's doing very well at? Where is it?
Yeah, so there is zero numerical analysis. There's not a lot of differential equations, but a little bit, and a lot of the and while there's not a lot of differential equations, a huge amount of the foundations are done, and like the operator theory is set up to do a lot of sort of general purpose differential equations theory in the future. The conspicuous area, low dimensional topology is conspicuously hard. I've tried a few times to define the Jones polynomial and been sort of disappointed that I haven't ever sent something to MathLib. For reasons I'm not entirely sure why that's proved difficult. Yeah, so those are some of the lowlights of things we're missing. The places where we're doing very well, there's a lot of algebraic number theory. There's a lot of commutative algebra. There's a fair bit of algebraic geometry, but like there's a long way to go there. There's a fair amount of category theory, but not much of like the last 10, 20 years of category theory, if that distinction makes sense. There's one interesting webpage. There's a list of the standard French undergraduate curriculum. And for every bullet point that we took from this government webpage, the corresponding MATLAB statement, if it exists. And that's that is one interesting way to see the coverage. The whole numerical analysis section is a big gap. But for a while, one of the goals has been we want to have the supremum of everything in an undergraduate course anywhere in the world. And we're still not there, definitely, but in many areas we're way beyond that. I mean, in commutative algebra and algebraic geometry and number theory, yeah. Yeah.
So if one tries to learn Lean as the programming language in one of the standard ways, which is to attempt the advent of code in it.
Yeah. No, so if you look on, one thing I didn't show you, one tab I had open here, was just Zulip. Anyway, it's super active. As you can see, well, I don't know. There are 800 new messages since last night when I last caught up. The list of green dots scrolls off the page. It's very active, and there's some. I could probably find it, but there's a stream of people talking about advent of code, so people are definitely doing it. I only did day one.
I've been finding it tricky to parse the inputs.
Yeah, it's definitely possible to do nicely. The parser tools in Lean 4 are very poorly documented, so you need to be a bit of an expert to do the parsing. The problems that I did, I really just I'm going to turn this into I'm going to take this big string and I'm going to chop it up on spaces and I'm going to do it the dumb way, with no attempt to do things efficiently. But if you look in the advent of code streams and you look in particular for Kyle Miller's solutions, he tends to be, he writes nice parsers that do things the right way.
I was hacking on a parser comment here this morning. I'd be happy to do it.
Yeah, this is something there's a big gap in the documentation of writing nice parsers in Lean 4. But the actual parser in Lean 4 is amazing. So it's definitely possible to do everything you want.
Great.
Okay.
Well, thank your speaker.